everyone. Myself Dr. Vijayakumar, Associate Professor, Department of ECE, Aditya University. In this session, we are going to see some more noise parameters. In the earlier session, we have seen noise parameters like effective noise temperature, noise equivalent bandwidth. In this session, we will be learning few more noise parameters like average noise figure and equivalent noise bandwidth concepts here. At the end of this particular session, the learning outcome 1 we will be learning is understanding the average noise figure. Learning outcome 2 is understanding the equivalent noise bandwidth. Okay. So, we will define what is meant by noise figure. So, generally when you take a two-port network, two-port network means a network which consists of 4 terminals, input terminals 2, output terminals 2. So, when you take a two-port network, the ratio of available noise power spectral density at the output to the noise power spectral density at the noiseless two-port network. When a network don't have any noise, that is the noise output power spectral density to the noise output power spectral density when a noiseless network is considered. So, the first numerator indicates whenever there is a noise, that is the noise power spectral density, and here whenever no noise, the noise power spectral density. The ratio of noise power spectral density at the output to the noise power spectral density at the noiseless two-port network is nothing but noise figure. Or else we also define this as signal to noise ratio at the input to the signal to noise ratio at the output. This definition is also valid when you express in terms of signal to noise ratio, and this definition is based on the noise power spectral density. And there are some cases where noise figure at a particular frequency is also known as spot noise figure. If you are interested in finding the noise figure at a particular frequency, this definition is called spot noise figure. This is also used in computing the gain of the network. Okay. Sometimes if you want to compute the gain of the network at a particular frequency, this concept is valid. But in reality, the average noise figure is obtained by the band of frequencies or from frequencies 0 to infinity. In general, when it comes to practice, we are more interested in the band of frequencies. So, generally it is quite useful to compute the average noise figure for a band of frequencies instead for a single frequency. So, many applications are related to the band of frequencies. There we compute the average noise figure. So, what is meant by average noise figure? So, already we defined this one in the previous sessions. The average noise figure is mathematically defined as input signal to noise ratio at the receiver to the output signal to noise ratio at the receiver. And if you want to express in decibels, 10 log 10 F. If there is no noise, assume in any system there is no noise, the noise figure will be mathematically equal to 1. In decibels, it is mathematically equal to 0 dB. So, F is equal to 1 or 0 dB indicates it is a noiseless device. So, the average noise figure quantifies the average degradation of signal to noise ratio due to the noise added over its entire operating bandwidth. So, it gives you the information regarding the how much SNR is degraded due to the noise over a entire operating bandwidth. It also represents how much additional noise is introduced into the system on an average. System in the sense it can be a receiver, amplifier or a network. How much average amount of noise that is coming into the picture or coming into the system. It is also generally represented as average noise figure. As earlier also we have seen, generally when we are talking about the amplifiers, when we are talking about the electronic devices, we cascade them. So, the output of one device will act as input to the second device, output of third device will act as, second device will act as input to the third device. Like this, there will be a cascading connection. So, cascading connection will be there. So, based on this cascading connection, we need to derive an average noise figure formula, which is very useful in solving the problems and analyzing the system. Assume a two-port network 1 and two-port network 2 are cascaded to each other, 1 and 2. Assume the noise figure of first network is F1 and gain is G1. Assume the second network noise figure is F2 and gain is G2. So this connection can be extended. So the total noise figure is mathematically given as F1 plus F2 minus 1 by G1, F3 minus 1 by G1, G2. We know what is F1, F2. These are nothing but noise factors at each stages, gains at each stages. So we will see how to derive this particular equation, how to derive this overall equation. So the total output noise power can be computed as follows. In the first case, amplifier source noise. The source itself will generate some noise, that is nothing but KTS/Bn. This noise power is amplified by the both stages and it produces the noise as G1, G2, KTS/Bn. And the first stage, internal noise generated by the first stage will be amplified at the second stage. So internal noise generated by the first stage is G1 NAS1 plus NAN1, and this is mathematically simplified and expressed like this. This internal noise will be amplified at the second stage by multiplying with gain G2. So internal noise will be generated by the second stage also. It is given as NAN2, and the total noise power at the second stage is due to source, due to first noise amplifier which is amplified, and due to the second source acting alone. Now the total or the average equivalent noise figure is noise figure when it is a noiseless network and whenever there is a noise to the noiseless network, noisy network divided by noiseless network. Noisy network means two stages I need to consider. So in the two stages the noise is source noise and first network amplified noise and second network standalone noise, and this is the total noise at the source when there is a noiseless two port networks. When you mathematically calculate, what you will get, F is equal to 1 plus TE1 by TS, TE2 by G1 TS. So we know what is TE1 and what all this. So we have seen in the previous noise parameter calculation, noise figure is expressed as 1 plus TE by TS. Based on that, TE1 is F1 minus 1 into TS, TE2 into F2 minus 1 into TS. On substituting, what we will get, F is equal to F1 plus F2 minus 1 by G1. So this result can be extended to n number of stages. When it is extended to 3 stages, let us say F1, F2 minus 1 by G1, F3 minus 1 by G1, G2, like this. The process will continue like this. The same formula can be used for computing the temperatures also. This we have seen in the previous session. The effective noise temperature is TE1 plus TE2 by G1 plus so on. It depends on number of stages. So this formula will be useful in computing the average noise figure for a cascaded network. Let us see one problem how to compute the overall noise figure for a network. Let us say an electronic system is taken which has an amplifier followed by a mixer stage, and the noise figure of amplifiers and mixer are 30 dB and 20 dB respectively. If the power gain of the amplifier is 10 dB, we are asked to calculate the overall noise figure. So the noise figure of amplifier is 30 dB, that means 1000. The noise figure of mixer is 20 dB, that means 100. The gain of the amplifier one is 10 dB, that is 10. So we know the formula, F is equal to F1 plus F2 minus 1 by G1. Here F1 is the amplifier noise figure, that is 1000, and mixer noise figure 100 divided by amplifier gain, we will get 1009.9. So if you want to express in dB, 10 log 10, 10 log 10, we will get 30043 dB. This is how we can compute the noise figure. Here we have taken an example with 2 stages which consists of amplifier and mixer. So this is another problem. It is also almost similar. F1, G1, F2, G2 is given and all data is given in terms of dBs, in terms of normal values. So F total is equal to F1 plus F2 minus 1 by G1. We will get 2.2. In dB we want to express, we will get 10 log 10 of this value, we will get 3.4 dB. And In the earlier session, we have seen the effective noise temperature. So, how to compute the effective noise temperature when the resistors are connected parallelly with two different temperatures. So, resistor R1 with temperature T1, resistor R2 with temperature T2. Assume a noise source is a current source. So, current sources parallel, same direction, we can add the current source. Parallel connection of resistors, R1 parallel with R2, R1, R2 by R1 plus R2. So, the overall noise will be IN square is equal to 4K TS BN into R equivalent. R equivalent is R1, R2 by R1 plus R2 or 1 by R1 plus 1 by R2. From this, what we will get is T1 R2 plus T2 R1 by R1 R2. This is the equivalent noise temperature whenever two resistors are connected in parallel. Very frequently we use these problems or these concepts in series and parallel. So, in this session what we have seen, we have defined the what is meant by noise figure, what is meant by spot noise figure, what is meant by average noise figure. So, noise figure in general we defined, spot noise figure is defined only for a particular frequency and average noise figure is used practically for a band of frequencies, for a band of frequencies. So, this average noise figure is generally used practically for analyzing the noise. So, in the next session, we will be seeing the spectral components of noise and we will analyze the noise in narrow band noise and wide band noise, and we will see the properties of narrow band noise in the next session. Okay, thank you.